If you could jump ahead in your PowerPoint notes to section Roman numeral 4, Le Chatelier's principle, we'll discuss what's happening in the lab that you're either currently involved in or will start in the next lab period. Le Chatelier's principle says if stress is applied to a system that's at equilibrium, the equilibrium will shift in such a way that reduces or relieves the stress. Now, stress in the chemistry world doesn't mean what you normally would think of as stress. Stress in their world is not the impending doom of a final exam, but if someone fiddles with one of three things, they could adapt or modify the concentration, they could possibly change the pressure if they're all gases, and if it's an endo or exothermic reaction, it can respond to changes in temperature or heat. So let's look at a famous process here, that Haber process again. Just so that you know, those two arrows that are opposing each other in a perfect world would be written one on top of each other, showing it's a reversible reaction. Now, if you look at the reactants on the left-hand side as kind of raw material, clearly, if I give you more raw material in the form of nitrogen by increasing its concentration, it will be able to combine with greater collisions of hydrogen to produce more ammonia. So, increasing the concentration of a reactant on the left-hand side shifts or drives the equilibrium to the right-hand side. Now let's talk about that shifts or drives or favors, that you're going to hear me use one of those three terms. If I say shifts right or drives right or favors products, you've done something in the form of chemical stress to push the forward reaction more towards the right, temporarily making more product until a new equilibrium is established. Remember, as product builds up, it will eventually break down and go back to making reactant. While I know that you know these reactions are reversible, by convention we call anything on the left-hand side a reactant and anything on the right-hand side we call a product. So let's take a look at if you had added some more hydrogen, for example. More hydrogen will be able to collide with the nitrogen molecules more frequently, and you drive to the right, making more ammonia. In the process, adding anything, for example, let's go ahead and talk about adding that hydrogen. More hydrogen concentration being increased will consume the nitrogen as the equation drives to the right to make some more ammonia. So let's look at the opposite of that. What if you had removed N2 from the left-hand side? Adding to a side drives it to the opposite side. Remember, there's no side in the beaker. Both forward and reverse reactions are happening simultaneously, but we're going to pretend that you could just add to the left-hand reactant side or remove from that. Well, if I take away some of this nitrogen, it's almost as if the ammonia that's there senses nitrogen is missing, and it says, you know what? I better hurry up and break down to try to form nitrogen to replace what that human took away, and in the process, I'm going to produce some more hydrogen until a new equilibrium is established. So if you remove nitrogen, you should shift or drive to the left, temporarily favoring reactants. That means as I drive to the left, I'd be increasing the amount of hydrogen, and I would also be decreasing the amount of ammonia because it's being broken down to replace the nitrogen that had been removed. Now, what if you remove a product from the right-hand side? Well, removing ammonia right here, and this is actually what happens in real life industry, it's like the nitrogen and hydrogen on the left sense that it's missing, they drive to the right to try to replace the ammonia that was removed. So removing from a side drives to that side in the equation, and so you would shift to the right. You would favor making more NH3, but you would end up decreasing the N2 and H2 because they're hurrying up to combine with each other to make more ammonia. All right, let's test yourself. Think about it. If you add hydrogen to the left-hand side first, which side would it drive to? Adding to a side drives it to the opposite side. If you said shifts to the right, you are correct. Adding hydrogen, however, will consume the nitrogen as it drives to the right to produce more NH3. So the little up and down arrows are just talking about increasing or decreasing amounts. Let's use the correct word. Let's talk about concentration. So all equilibrium reactions are sensitive to changes in concentration. However, if all of your reactants and products are gases, they're also highly responsive to changes in pressure. It's a very simple rule. If you increase the pressure, it will favor a smaller volume. I have a container that's collapsible. I squeeze down on it. So I'm going to cram those molecules in close to each other. And what happens is that your equilibrium shifts to whichever side has the fewest number of molecules. So what you need to do first is then accounting. On the left-hand side as written, there is 1 mole of nitrogen molecules and 3 moles of hydrogen. On the right-hand side, remember this only works for gases. If they're all gases, there are 2 moles of ammonia molecules. So there's a total of 4 molecules on the left and a total of 2 on the right. Increasing the pressure will go to whichever side has the fewest molecules. Which way would this equilibrium shift? To the right. And in fact, again in industry, to make more ammonia, which is the feedstock for things like fertilizer and sadly bombs, it shifts to the right because there's only 2 moles of ammonia, and that's what they do in this Haber process. They make it happen under higher pressure. If you had released this pressure, now it will go to the side with the greater number of molecules. It would go back to the left until a new equilibrium is established. So pressure is the second stressor that you can apply to a reaction. The third is temperature. And to be able to understand the impact of temperature, first you have to identify if your reaction is endo or exothermic. For example, the reaction at the top shows energy being given off almost as if it was a product. Energy is being released. That's an exothermic reaction. If you had wanted to express it as an endothermic reaction, you could put heat on the left-hand side. But going from left to right, it's exothermic, and right to left, it would be endothermic. No, I don't want an update for my Adobe. Don't you just love Adobe? So, how do you figure out which way reactions will shift? I always have to have the same starting point for my brain. The beauty and the evilness of equilibrium is that you're either 100% right or 100% wrong because they're 50-50 answers. So I always start with an endothermic reaction. An endothermic reaction needs heat to go. So if I give heat to an endothermic reaction, it goes, yay, I'm going to drive to the right and make more of my product. So heat could be thought of as a reactant on the left-hand side. However, if it's an exothermic reaction, like the one we can see here, heat is on the right-hand side. To get it to drive to the right, you want to chill it down. You could keep pulling away that energy that you can see on the right-hand side, keep removing it, and the left-hand side says, hey, wait a minute, somebody's removing one of my energetic products, we'll still keep driving to the right. So it's a little confusing, but I think if we can get to a picture that demonstrates how to understand it, it will also complement what we've learned in the lab. But I always start with, if it's an endothermic reaction, adding heat drives it to the right. Removing heat from an endothermic would drive it to the opposite, back to the left. And if exothermic is the opposite of endothermic, adding energy essentially means you'd be adding something to the right side, so you'd be driving back to the left. So if I really want an exothermic reaction to happen, I chill it down. I keep removing heat to keep it driving to the right. Now we haven't discussed equilibrium constant at this point, and so I'm just going to have you go ahead and figure out on our next couple of slides what's happening with our endo and exothermic reactions. But for now, just go ahead and write down that if you do change the temperature, you will change this thing called the equilibrium constant. It's just a number, and the size of the number tells you who is favored at equilibrium, reactants or products. Changing the temperature always changes the equilibrium constant. concentration and pressure changes will not have any impact on the equilibrium constant. And as you'll see on the third and last vodcast, it's a very simple calculation to do. So let's look at a picture of what's happening when you use the cobalt reaction. Now, if you were superhuman vision and could see inside these containers, if you see a predominance of a blue color, that means you're looking at the COCl4 ion. That should have a 2- charge up there. So if you see blue, you're seeing more of these blue cobalt chloride ions forming. There are still a few pink cobalt with the 6 waters attached. In this beaker in the center, it's got a little heat that must have been added. If you look carefully, you can see some condensed steam on the inside of that beaker. And the beaker is a water bath that's chilling or heating that test tube full of cobalt ions in the middle. So obviously heating this reaction produced more of the blue form of cobalt chloride. And as you see the equation written here, it must have been driving our reaction to the right. If, however, your eyeball sees a pink color, that means more of these weird cobalts with 6 waters attached to them must be dominating the equilibrium. There's still an occasional blue, COCl4, but pink is only achieved by removing heat. See the ice cubes floating in that beaker? So apparently heating it drives it to the right, chilling it drives it back to the left. The far, far left beaker looks kind of purple because, as you can see, they have it at an intermediate temperature between too hot and too cold, and so there's a fairly equal amount of cobalt ions of both forms. Let's take a break and watch a very short YouTube video, which I will attempt to narrate. And what we have here is a YouTube on a YouTube. Let's go ahead and play that, which started out as being all pink. So a YouTube is an actual glass tube. So a YouTube on a YouTube here. And that pink color is formed when you take some of these really pretty cobalt chloride crystals and dissolve them in water. You're going to pour, in this YouTube video about a YouTube, some of that pink solution in. At this point, the cobalt with the 6 H2Os attached must be dominating. The beauty of the YouTube is that you can heat just one side. And as you heat that side, you see it begins to go purple. And then if you continue to heat that side, it gets to be an even deeper blue. If you're seeing a blue color, then you must be forming the COCl4 ions. So adding heat is going to drive your reaction to the right, producing more blue COCl4 ions. For me, that must have been an endothermic reaction as written. Now I'm going to stop there because the video would go on with some more Spanish classical music, which is quite lovely, but we need to finish the podcast. And so let's go ahead and do that. Whoops. I need to go back to my podcast. So back to our vodcast then. Here's another picture of the situation that we just saw. At room temperature, you have a purple solution because you have significant amounts of equal amounts of the cobalt with 6 waters and the cobalt with 4 chlorines or chlorides. But heating it will drive this reaction to the right, forming more blue COCl4 2-, and cooling it shifts it to the left, forming more of the pink cobalt with 6 waters. So what kind of thermic do you think this reaction is? If heating it shifts your equilibrium to the right, it must have needed heat to go to the right, and that would be an endothermic process. So that's the last stressor. We just want to make a mention that you can use a catalyst in any kind of reaction, even one of these reversible, and essentially all that happens when you use a catalyst is it allows you to reach equilibrium more quickly. It doesn't change the equilibrium concentrations, you just get there sooner. Because of course, you reduce the activation energy. Well, that's it for this vodcast on Le Chatelier's principle. In the third and final vodcast for the chapter, we'll discuss the equilibrium constant. Until next time.